Hello everybody, welcome to the Soil Physics Lab of Lal Carbon Center at the Ohio State University. In this video, I am going to demonstrate how to measure plant available water capacity using field capacity and permanent wilting point measurements. This is a live laboratory demonstration where I'll show soil core saturation, tension table measurements for lower section, for example 10-20 centimeter section, and pressure plate measurements for higher sections including permanent wilting point. And finally, we'll show how to calculate the plant available water capacity using those measurements. Firstly, let me talk about why plant available water capacity is important. Plant available water capacity represents the amount of water in soil that plants can actually absorb. It's defined as the difference between water held at field capacity and water held at permanent wilting point. This range represents the physically and biologically available water for plant roots. Let me talk about the theoretical background of soil water potential. Soil water is retained in soil pores due to matric forces, for example, capillary forces and adsorption forces. As soil dries, water is held more tightly and plant must extract more energy to extract it. That's why we express soil water status in terms of soil water tension or suction. Then what are the definitions of field capacity and permanent wilting point? Field capacity is the soil water content after excess gravitational water has drained. Macropores are mostly empty. Micropores and mesopores retained water. In laboratory measurement, field capacity is typically determined at -10 to -33 kilopascal depending on soil texture. Permanent wilting point is the soil water content at which plant can no longer extract water. Even after re-watering, plant don't recover. In the lab, it is measured at -1500 kilopascal suction using a pressure plate apparatus. Here we are using undisturbed soil cores. You could see here the cores are collected carefully to preserve soil structure, and the core is saturated slowly from the bottom by capillary rise. So we added water in this tray gradually so that capillary actions work here. This prevents air entrapment and ensure uniform saturation. Capillary saturation mimics natural wetting condition here. Once fully saturated, the cores are ready for tension based measurements. This is our tension table measurements apparatus. You can see here is a stand and it holds the water column here, and these are our samples. The setup includes a saturated porous surface here, a connected water column you could see here, adjustable suction controlled by height of the water column. When we will change the water column height, it will also change the suction for the soil cores. This instrument is used to measure soil water content at low suctions, typically relevant for field capacity. Let me talk about how the water column works here. The vertical water column, you can see here, it controls soil water suction using hydrostatic pressure. 1 centimeter height of water column is equals to 1 centimeter of suction. Lowering the water level increases suction. Rising the water level reduces the suction. Why tension table is used for field capacity or low suction measurement? The tension table is ideal for measuring field capacity because it targets macropores and mesopores. It applies low controlled suction. It closely mimics post-rainfall drainage condition. Once equilibrium is reached, drainage stops, soil water content represents field capacity. The next step is equilibration and weighting at field capacity. After equilibrium, like No water drop would come from here, so it's equilibrium. After this equilibrium, soil cores are removed, excess surface water is wiped off, cores are weighted immediately. Basically, we use the tension table measurements for up to 60 or 80 centimeter suctions. But after getting that measurements, we use this pressure plate apparatus for the original field capacity. For example, minus 33 kilopascal pressure here, and then for permanent wilting point we use minus 1500 kilopascal pressure. Let's talk about the pressure plate apparatus for field capacity and permanent wilting point. To determine field capacity and permanent wilting point, soil cores are placed on a saturated ceramic plate here inside a pressure chamber. Like you can see, here is the inside of that pressure chamber, and this is the lead. We can add different plates, up to around 4 plates in the chamber, and this is the outlet. From here the water would come after getting the pressure, and this is used to control the pressure in that chamber. And we also have this apparatus, it's for the permanent wilting point. We can add up to 2 plates in that chamber, and then this is the lead. We use this to tighten the chamber. Unlike the tension table, this method applies air pressure. Like you can see, these are the cylinders and we have nitrogen gas here to use the air pressure, and that is used for high suctions. Now let's talk about how pressure plate works here. When pressure is applied, air pressure forces water out of the soil pores. Water exits through the ceramic plates. Only water held in very small pores remains. At 15 bar, water is tightly absorbed. Plants can no longer extract it. This corresponds to the permanent wilting point. After equilibrium at each suction, soil cores are weighted, then oven dried at 105 degrees Celsius, and then dry weight is recorded. Water content is calculated on a volumetric basis using bulk density. Calculation of plant available water capacity. Plant available water capacity is calculated as the subtraction of permanent wilting point from the field capacity. FC, that is field capacity, volumetric water content at field capacity, and permanent wilting point, that's the water content at permanent wilting point. This value represents the water accessible to plant root. Let's talk about the pore size distribution. Different pore sizes play different role. Macropore, it's very essential for drainage. Mesopore, that is plant available water, and micropore, that is totally unavailable water. Plant available water is primarily controlled by mesopores, which are strongly influenced by soil aggregation, organic matter, long-term management practices. What could be the interpretation of the results? Higher plant available water capacity indicates better drought resilience. Well-structured soil retain and release water more efficiently. Organic amendments and stable aggregates often increase plant available water capacity. Plant available water capacity integrates soil structure, pore continuity, and soil carbon effects. This is how plant available water capacity is measured using tension table for field capacity or lower sections, and pressure plate techniques for ultimate field capacity like minus 33 kilopascal and permanent wilting point. Thank you so much for watching this video. Please like, share and subscribe for more content on soil physics, soil water and soil health.